G'day all and welcome to our series of lab videos for physics. This morning we're going to spend a bit of time on the specific heat of metals. Specific heat essentially being the amount of heat energy that it takes to change the temperature of something by a certain amount. So every material has a specific heat, and it's part of understanding the distinction between heat and temperature. Temperature is a measure of the amount of energy, but because objects take up heat differently, they'll have different specific heats, and it will take a different amount of energy being added to change the temperature of something. So we're going to work with four metals. We've got some aluminium, some zinc, some tin and some copper. And what I'll do for this video is just show you the procedure for one of them, but what we're actually going to do is test each of those and find the specific heats of each of those different metals, and then we're going to use that to actually calculate the ways in which those metals differ from each other in terms of their properties. The things that dictate the specific heat will be things like how the particles are bound together. So the metallic bonding inside, the nuclei, the electrons, how those are interacting will determine how much heat it takes to heat something up. Now we know that water takes about 4.184 kilojoules per gram to heat up. So we're going to use the specific heat of water in order to test the specific heat of the metals. So this is how we'll do it. We will get a cup full of water. We'll take our cup and we'll measure its mass first. You'll notice that I'm writing in my lab book, and I'm writing everything in my lab book. Your lab book basically is not your final lab report. You'll submit your final lab report online. Your lab book is, here's where I capture the data. So I need to have every piece of data that I need to be able to write up the report in my lab book. We're going to actually give you the data for this lab so that you can do the calculations and the full write-up, despite not having been able to do the lab. Although, to be fair, this one probably is fairly feasible to do at home. You don't necessarily have a Bunsen and a beaker, but you do have a saucepan on the stove, and that would work for the purposes of this. You would need a styrofoam cup, which is not too hard to get hold of, and you would need a thermometer. So you could potentially do this experiment at home. So I'm going to measure the mass of my cup first, and it's 1.72 grams. So that's 3 significant figures, 2 decimal places. Hang on, once it settled down, it said 1.71, so I'll correct that. And then I'm going to partly fill it with water at the tap. And I'm going to weigh it again, because what we're going to do is check the amount of energy that water picks up. We need to know how much water we've got. So it's 140.44 grams. So I've written that down. I've written M of cup equals 1.71 grams. I've written M of cup plus water equals 140.44 grams. So I now know the mass of water that I've got if I subtract one from the other, because the cup is only a very small proportion. I'm going to put it in this guy, which is, we call a calorimeter. It's really just a styrofoam block. And the goal is to stop us losing any heat. What we want to know is to be able to keep track of the heat that we've added to the system. And obviously, if it was being radiated out from the cup, that would be a problem. So we're trying to keep as much heat in as we've got. We've got a styrofoam box with a styrofoam lid around a styrofoam cup. So it's not perfect, but it's pretty good. We could have a thermos if we wanted a really good one. So what we're going to do is heat our sample of metal to a known temperature. So in this case, I've got my lump of copper. I'm going to submerge it in some water that will shortly be boiling. I've prepared it earlier so that we could get started, and that's hot. And what I want to do is submerge it, hang it there, not on the bottom, in the middle, and I want to leave it hanging there for about 5 minutes, because I want the temperature to be the same all the way through the block of metal. So we know that copper is a very good conductor of heat, so it's not going to take very long for the heat to go all the way through. So we're going to end up with the metal at the temperature of the water. Now we can't measure the temperature of the metal directly, it's a bit difficult, but we can measure the temperature of the water. So we've got the thermometer in the water. It's currently reading 96. I've got to get down for parallax error, 96 degrees, 0.0 really. I'm going to assume at this point, because my fingers are getting hot, that that's the temperature of the metal. My block of metal is at 96.0 degrees Celsius. I'm going to put it in my calorimeter, and then I'm going to pop the lid on, and we've got a temperature probe here. So we're measuring the temperature of the water. We needed the initial temperature of the water, which I should have taken before I popped the thing in, 22.6 degrees. So I need to write down two things. Temperature of the metal, T metal, is 96.0 degrees Celsius, and T water initial, you can use whatever subscripts you like on that, was 22.4 degrees C. And what we're going to do now is just wait for this block of metal and that water to equilibrate, to come to the same temperature. So what's happening is heat energy is flowing out of the metal and into the water. And what we want is them to come to the same temperature. Because when they come to the same temperature, we can figure out how much heat energy has gone into the water, and that's the amount of heat energy that's come out of the metal. And we will know the change in temperature of the metal, and we know how much heat energy has come out. So that gives us the specific heat of the metal. So that's what we're actually working on. And this probeware will allow us to actually measure the temperature curve of the water, because it's probably going to get hotter and then start getting cooler, probably slowly because we've got all that styrofoam, but it'll start getting cooler over time. We want that peak because we want to know the exact moment at which the two things are in equilibrium with each other. This is the calculation of the specific heat of copper specifically. Now, we had 4 different metal cubes there, so we're going to actually give you the data for each of the 4 in terms of their masses and their initial temperatures and final temperatures, and then your job is to do the calculations for all 4. But I'm going to run through the copper one, which is the one we did in the experiment video, as an example. And then obviously the procedure is similar in both cases. Now the mass of the cup was 1.71 gram. The mass of the water was 140.44 gram. You'll note here that we are working in grams rather than kilograms. We could work in kilograms as the base SI unit, but it turns out that everywhere we would put it in, that's going to cancel out and give us an answer that will work in grams anyway. And also the specific heats that we need to know and the ones that we're going to find out are also often expressed in joules per degree per gram. So in this case, specific heat of water, which is what we need, so I'm going to be consistent and keep writing water rather than H2O, is 4.18 joules per gram degree Celsius. So a gram times a degree Celsius, joules divided by that energy. So it's the amount of energy required to heat 1 gram of the substance by 1 degree Celsius or 1 degree Kelvin. The two are the same. Again, we could use Kelvin as the most fundamental unit, but every time we use them, we're going to subtract one temperature from a different temperature. So using Kelvin, we would add 273 to both, but then we subtract that factor of 273 would just disappear. So we're quite happy to work in degrees Celsius. The only time we wouldn't is if we were going from below 0 Celsius. Then it gets difficult and it's better to work in Kelvin. But for our purposes for this experiment, we're quite happy to continue in degrees Celsius. So the thing that we're trying to find is C, the specific heat of copper metal, and we don't know what that is yet. That's our actual finding, same units. So that means that the mass of the water is just that's water plus cup. Didn't do that quite right. Mass of the water is equal to that minus that, which is 138.73. Now the other thing I'll note is that we are doing measurements to particular precisions. So in this case, because we had a balance that worked to 2 decimal places, we can do our measurements to 2 decimal places. That's quite a high level of precision, but we should really propagate our errors all the way through. This time I'm not going to, because I'm going to work on this particular one. There are other experiments in which we do propagate errors all the way through, but if we were being even more precise, we would say plus or minus 0.05 gram, because our balance is usually what we do is a half of the least scale deflection. No, I have one too few zeros. So if our balance is giving us down to 2 decimal places, we need a half of 1 division of that. So that's 5 to, at the third place, 5/1000ths is a half of 1/100th, if that makes sense. So that's the level of precision that we're working to, and the temperatures are nowhere near that. Our temperature probes would only give us 1 decimal place. So we're working to precisions in the thousandths with our masses, but only in the hundredths with our temperatures. So that's a difference of accuracy that we've got. We've got the mass of the copper that we've got. It was a 2 centimeter cube, and its mass was 71.68 grams. So what we did was heat the copper to a certain temperature and then drop it into that mass of water, the 138.73 gram. The copper got cooler and the water got hotter, and they eventually met at a particular temperature. So let's see. T water initial, and we're getting too many subscripts. The original temperature of the water that we got from the tap was 22.4 degrees C. The original temperature of the copper was 96.0 degrees C. Remember, it was suspended in boiling water, so 96.0 degrees C. And the final temperature we got, which was the temperature when they'd come to equilibrium, so it's both of them, final temperature was 25.6 degrees C. Oops, 25.6 degrees C was the temperature that we got for both the copper and the water when they'd come to temperature. Now, we were measuring the water, but we assumed that given enough time, the two would come to a thermal equilibrium. And we weren't losing much heat because we had a styrofoam cup in a styrofoam box. So the amount of heat being lost was fairly negligible in that particular measurement. So what we want to do is calculate the amount of energy that was gained by the water initially, use that to then calculate the amount of energy that was lost by the copper, and from that we will know how much energy there was in the copper that has been lost. In other words, how much energy it takes to change the temperature of the copper from 96 down to 25.6. So let's work on how that works. So we have the equation delta H, which is the change in heat of the thing that's happening. Delta H equals M, the mass of the substance that you're looking at, times C, the specific heat of that substance, times delta T. Delta T is the change in the temperature. So the mass of the water that we had is 138.73. The specific heat of water is 4.18 units, joules per gram degree. And the change in temperature is, it started at 22.4. Just trying to think about which is the best way around to do this. Let's consider that when something gains heat, it's a positive number, and when something loses heat, it's a negative number. So in this case, the water gained heat. So to do the delta, we'll subtract the larger from the smaller from the larger. so that we end up with overall a positive number. This is the amount of energy that was gained by the water from the metal. So we'll end up with a negative number for the amount of energy that was lost by the metal. So if we run that through a calculator, we'll end up finding that the amount of energy gained by the water was, sorry, give me 1 second for my handy dandy calculator, rose by 3.2 degrees times 4.18 times 138.73 equals 1,855.65. Now, no, too much precision, because I've got 2 decimal places here and here, but only 1 decimal place here. So my answer should be to 1 decimal place. So 1855.7. And remember that the unit of that is joules. So we've got joules equals grams times degrees times, grams times C times degrees, change in degrees. We could actually do a full dimensional analysis on that, but maybe trust me that works, or run it yourself. So basically, on one side you've got heat, joules, the unit of heat. On the other side you've got some mass and some temperature, but they're on the bottom line and joules on the top line, so it all cancels out and works. So that was the change in energy of the water. So delta H water, I probably should have subscripted it up here as well, is that much energy. That much energy was gained by the water in the process of rising by 3 degrees. So the key concept here is that the same amount of energy was lost by the metal. So there's no external source of energy. It's well insulated. So we didn't have a Bunsen under it, or we didn't have refrigerator coils or whatever. Okay, on a new page, just for neatness, we have delta H of water is equal to 1855.7 joule. Now the delta H for the copper is going to be just minus that, because overall energy is conserved. So the energy that's gained by the water is the energy that was lost by the copper. So that's the energy lost by the copper. Now what we want to do is calculate the specific heat of the copper. So we have the expression delta H equals mc delta T. We want to rearrange that to make C the subject, because we're calculating the specific heat of copper. So C equals delta H, and then we divide by both sides by M and delta T to get C by itself, M delta T. Apologies if my deltas sometimes look like A's. So the delta H we just calculated is minus 1855.7. The mass of the copper is 71.68. The temperature change is from 96 down to 25.6, but it's going to end up as a negative number. Specific heats are always positive numbers, and it was an energy loss. So the delta is the reverse of that effectively. So if I run that through a calculator, I will get an answer of 0.368 joule per gram degree C. So that is C, the specific heat for copper that we've actually calculated. Now, we could have, as I say, propagated our errors all the way through, or our uncertainties all the way through is probably a better way to say it, but we didn't. But then we would know how precise and accurate our answer is. I looked up the specific heat of copper, so this is our experimental determination. I looked it up earlier. For copper, the specific heat in the literature is 0.385 joules per gram degree Celsius. So that is from the literature. So certainly in your write-up you can compare that value and look at the other experiments that we've done as well. Talk about possible sources of error and issues that might have explained those differences and so on. But we're in the ballpark. We're not times 10 or divided by 10. We're not several orders of magnitude out. We are, a few percent off, which is, completely acceptable for normal physics experiments. So I hope that was helpful. I hope it gives you a sense of how to calculate these. And as I say, you can go ahead and use the data that we're sharing with you to calculate the values for the other metals, aluminium and zinc and so on. Thanks very much.